Nuclear fusion is a process in which two atomic nuclei come together to form a heavier nucleus, releasing a significant amount of energy in the process. This process powers the Sun and other stars, as well as hydrogen bombs. In more technical terms, fusion occurs when two light atomic nuclei, typically isotopes of hydrogen, such as deuterium and tritium, collide at high speeds and temperatures with enough kinetic energy to overcome their mutual electrostatic repulsion and get close enough for the strong nuclear force to bind them together into a single, heavier nucleus. This new nucleus has slightly less mass than the combined masses of the original nuclei, and the missing mass is converted into energy according to Einstein's famous equation, E is equal to m times c⁻². The energy released from nuclear fusion is several times greater than that released from nuclear fission, the process used in conventional nuclear power plants. Fusion has the potential to provide a nearly limitless and clean energy source. Unlike nuclear fission, fusion doesn't produce long-lived radioactive waste or emit greenhouse gases, making it a promising candidate for addressing future energy needs and reducing reliance on fossil fuels. It is theoretically possible to generate electricity via nuclear fusion. However, achieving practical and sustained nuclear fusion for electricity generation is still a complex and challenging endeavor that researchers and engineers are actively working on.
If this is the first time you are visiting our channel, please make sure you hit the subscribe button.
To generate electricity through nuclear fusion, scientists aim to replicate the conditions found in the core of stars, where fusion reactions naturally occur. This involves creating and maintaining a high-temperature and high-pressure environment where atomic nuclei can collide with enough energy to overcome their natural repulsion and fuse together, releasing energy in the process. There are several experimental fusion reactor designs being developed to achieve controlled and sustained fusion reactions. Two of the most prominent designs are tokamaks and stellarators. A tokamak is a donut-shaped device that uses magnetic fields to confine and control the superheated plasma of hydrogen isotopes, like deuterium and tritium, needed for fusion. The magnetic fields keep the plasma away from the walls of the reactor, preventing it from touching and cooling down. The International Thermonuclear Experimental Reactor Project is a notable example of a tokamak-based fusion experiment aimed at achieving self-sustained fusion reactions and demonstrating the feasibility of fusion as a viable energy source. Stellarators are another type of magnetic confinement device designed to maintain a stable plasma state for longer periods by using twisted and complex magnetic fields. Stellarators are known for their ability to avoid some of the instabilities that can arise in tokamaks. They are more challenging to design and construct than tokamaks, but they offer potential advantages in terms of steady-state operation. In addition to these reactor designs, various diagnostic instruments, sophisticated control systems, and advanced materials are required to achieve the necessary conditions for nuclear fusion and to safely harness the generated energy. While significant progress has been made in recent years, practical fusion power plants that can generate electricity on a commercial scale are still in development. Challenges include achieving the necessary temperatures and pressures for fusion, sustaining the plasma for extended periods, managing the intense energy released during fusion, and dealing with radiation and other engineering issues. Researchers remain optimistic about the potential of nuclear fusion as a clean and abundant energy source, but there are still significant scientific and engineering hurdles to overcome before fusion becomes a viable and scalable solution for electricity generation.
Do not forget to subscribe to our channel.